So, welcome again to this new lecture of Fundamentals and Application to Electric Ceramics. So, let us briefly recap the past lecture. So, in the previous lecture we initiated our discussion on linear dielectrics, and we introduced terms like polarization, dipole moment. So, essentially linear dielectric is a material which is first of all insulator. So, a dielectric is by definition an insulator, okay. So, which means it has low conductivity. What it basically means is that when you apply electric field, it does not have long range motion of charges, it has short range motion of charges, and this short range motion is one which gives rise to what we call as dipole moment. So, a separation of charges plus q and minus q. So, this when you separate them by a distance, let us say d or delta, then you develop a dipole moment, that is mu, and this mu dot delta is the q dot delta is the mu vector that you get, and this polarization is nothing but all the sum of all the dipole moments in a given material divided by the volume, which is nothing but equivalent to surface charge density as long as polarization is perpendicular to the surface, and the unit of this is in coulombs per meter square and this is in coulomb meter. So, naturally when you have coulomb meter per unit volume, which is meter cube, you will get coulomb per meter square. So, and then we looked at the case of parallel plate capacitor. With a dielectric, and there we found that if you have a dielectric material with strength kappa or epsilon r, which is more than 1, when you insert it in a parallel plate capacitor, it enhances the capacitance by amount epsilon r or kappa multiplied by C naught. C naught is the capacitance of parallel plate capacitor in vacuum, and epsilon r is the dielectric permittivity or dielectric constant of. So, this is basically dielectric constant, and C naught is the capacitance of in vacuum, a free space, okay. So, this is something that we worked out, and so C is equal to basically you can say epsilon r epsilon naught A over d, that is what the, and you can also write this as kappa. So, it's a choice that we make sometimes. So, essentially when you now make a plot of, let us say Q versus V for a material, for a capacitor, Q versus P. So, let us say Q versus P for a vacuum is something like this, let us say, okay. Q is equal to CV. So, as you increase the voltage, you increase the charge, and when you have a dielectric material, as you keep increasing that epsilon r increasing, so as you increase the epsilon r value, so for this it would mean epsilon r is equal to 1. So, as you keep increasing the value of epsilon r more than 1, you keep basically for the same voltage you increase the charge storage capacity. So, you can say that for same capacitance you will reduce the voltage, or for the same voltage you will increase the charge storage capacity by using a dielectric by the amount epsilon r or kappa, okay. So, now let us see, so we introduce some more things. So, now we introduce the concept of what we called as dielectric displacement. So, dielectric displacement, so when you have a dielectric material, the presence of electric field causes the bound charges in the materials to slightly move away from each other, to slightly separate. So, as we said that you have when you apply electric field, the plus q and the minus q centers move away from each other by a distance, tiny distance, creating a dipole moment when you apply electric field, and this gives rise to what we call as local electric dipole moment. So, correspondingly you have a quantity called as dielectric displacement, or it is also called as electric displacement field. This quantity is called as d. Okay, d is a vector, and this d is defined as epsilon naught E plus P. So, essentially when you do not have a dielectric, when you do not have the dielectric material, so without a dielectric material, d will be equal to epsilon naught E, that is d naught, and when you insert a dielectric material, you induce a surface charge which is due to the presence of the material, a term called as polarization, which modifies the dielectric displacement by amount P. So, this P is the added quantity. So, you can say P is the macroscopic. So, epsilon naught is the permittivity of free space, E is the field that you have applied, and P is the, it's a macroscopic density of, you can say, permanent and induced dipole moments in a material. Okay, and this is also called, it can also be defined as polarization density, often it is called as polarization density. So, and this displacement vector d is also defined by Gauss's law. So, if you apply Gauss's law to a dielectric, so dielectric displacement has to satisfy the Gauss's law. What it means is that del dot d is equal to rho minus rho b, which is equal to rho f. What are these rhos? Rho f is basically, you can say, number of free charges per unit volume. So, basically charge density. Okay. Rho b is essentially, you can say, density of you can say dipole bound charges. Okay. And so, basically you can say from this rho is equal to rho b plus rho f. So, the net charge density rho is equal to the number of free charges per unit volume plus number of bound charges per unit volume, and it is a difference between the total charge density and the bound charge density, which is nothing but the free charges present on the surface, and that is what is Gauss's law, which basically Gauss's law says that it basically relates the distribution of electric charges as a from the applied electric field. Okay. So, you can see that this is dielectric displacement is related to electric field as we saw earlier, and this is related to the surface charge density. So, this surface charge density, for example, you can take in spherical cases, the bound surface you can take, or there are a variety of cases you can take, but it could be basically a enclosed spherical surface in this case. So, now let us say let us do a little bit of a proof of the previous equation. So, we said that D is equal to epsilon naught E plus P. Okay. So, this P is the polarization term which adds on to the dielectric displacement. If you did not have a dielectric material, then D will be equal to epsilon naught E. Okay. And when you insert a dielectric material, then D becomes epsilon naught E plus P. So, let us see what is the can we prove it. So, we said that total charge density rho was equal to the free charge density plus the bound charge density. So, we said rho F plus rho B, this is free and this is bound. Free is the free charge that is present on the surface of the parallel plate, right, and B is the charge that is bound because of presence of dipoles in the material. So, as we saw that you had initially 8 charges, out of 8 6 get bound and 2 remain free. So, basically total is equal to rho F plus rho B, alright. So, now if we write this as a function of polarization, so rho can also be written as rho F and this rho B is nothing but del dot P. Rho, so this is basically you can say the polarization is basically, so P is basically defined to be a vector field whose, if you take the divergence of this vector field, you will get the density of bound charges. So, P is related to the bound charges, and by definition this rho B is equal to del dot P. So, divergence of P is equal to nothing but minus of rho B. So, if you take now del dot E, so del dot E is equal to 1 over epsilon naught into rho. Where does this come from? This is the divergence of electric field should be equal to charge density basically. This is what is the law, this is called as, this is from Gauss's law, right, or you can say Poisson's law as well, it is also defined as Poisson's law. So, this is nothing but now 1 over epsilon naught into what is rho now, rho F minus del dot P, okay, and as a result you can say del dot E plus E plus P divided by epsilon naught, this is equal to rho F divided by epsilon naught. Alternatively you can say del dot epsilon naught E plus P is equal to rho F, and this is what is the original definition is. We said that del dot D is equal to rho F. So, basically what it means that D is equal to epsilon naught E plus P. This is what we wanted to prove, that the dielectric displacement is equal to the product of epsilon naught E plus the polarization, which is because of bound charges in the material. So, this is the additional effect that you create by inserting a dielectric in the parallel plate capacitor. So, we say that D is equal to epsilon naught E plus P, and after inserting the dielectric, what is the dielectric displacement? This is nothing but epsilon naught into epsilon R into E. So, from this we can say that P is equal to epsilon naught into epsilon R minus 1 into E, or we can say this will become, so this is what is the essentially polarization, and this is, and we define this as P is defined as chi into E, where chi is the dielectric susceptibility. So, essentially what you need to know to begin with, if you know concepts such as what is Gauss's law and what is Poisson's law, then you will be able to appreciate this. The Gauss's law says that the divergence of D must be equal to the surface charge free charge density, and So, that is, and then we from this we moved on to, we said that this is del dot D is equal to rho f, and then we know that total charge density is equal to surface charge density plus bound charge density, and hence, and this bound charge density can be written in terms of polarization as minus del dot P. Divergence of polarization is nothing but the bound charge density. You have to add a minus there to account for the signs to get the correct sign. So, rho B becomes minus of del dot P, and then we substitute, we get del dot E, and we know that rho F is equal to basically del dot E. So, this is nothing but so del dot E for a dielectric is, so we have taken, now we have a dielectric inside, right. So, we have a dielectric inside. So, the field inside the parallel plate capacitor with the dielectric will be del dot E. This del dot E is equal to rho divided by epsilon naught, and this is 1 over epsilon naught into rho f minus del dot P, and accordingly we make the terms move right and left side, and we get expression D is equal to epsilon naught E plus P. Okay. So, this is what basically the so del dot, basically you can say that del dot D is equal to rho. This is what the general relation is. So, here we have taken we have taken one something, it's nothing but this is equal to rho and this is equal to rho B plus rho F. Yeah, that is how it should be. Okay, because you are taking divergence, you are taking with respect to the all the charges that are present. So, that was a little. All right. So, now we have defined a quantity called as dielectric susceptibility, which is nothing but epsilon r minus 1. So, more the dielectric constant is, more the susceptibility is, and basically this is what is the response of the material. So, you can say that polarization is nothing but you can say chi is equal to P divided by epsilon naught E. This is also one definition of pi. So, basically it is a ratio of polarized charge. So, this is the polarized charge because of bound charges, right, to the excess charge that is present on the surface of a vacuum plate capacitor. So, this is the polarized charges because of dielectric to the bound excess charge, excess free charge on the plate. Okay. So, higher the epsilon r is, more the polarized charges will be, more the response of the system will be. And by the way, these quantities are vector in nature. So, we know that P is vector in electric field is vector. Okay. Polarization is a vector. As a result, the dielectric constant becomes a second rank tensor. Okay. So, this is a vector is a rank 1 tensor. So, polarization and electric field are rank 1 tensors. As a result, due to, since P is equal to epsilon naught into epsilon r minus 1 into E, this term basically becomes the, so here you can take you can say this will be epsilon naught epsilon r minus epsilon naught into E. This will be epsilon minus epsilon naught E. So, permittivity will be a second rank tensor for a dielectric material. Okay. So, now the question is, what is the microscopic reason of this polarization in the material? So, right now we have seen that it is because of separation of charges, but in a given material the separation of charges can happen at various scales. Okay. So, that is what we will look at now, and we will also, since most dielectrics are used not in DC applications but in AC applications under the effect of alternating electric field, as a result we also need to look at the response of this polarization or dielectric constant as a function of frequency of electric field, and this is because the microscopic mechanisms of charge, the dipole creation or polarization creation is also there could be multiple scenarios in which the charges which are involved, they may have different weights, different masses. As a result, they will have different responses to frequencies of applied field. So that is what we will look at now. So now we are going to look at what is called as mechanism of polarization. So essentially, microscopically speaking, there are 4 mechanisms. The first one is called as electronic polarization. Second one is called as ionic polarization. Third one is called as dipolar polarization, dipolar, or we can say orientation polarization. And the fourth one is called as interfacial polarization. Okay. So what is electronic polarization? Electronic polarization happens at the level of so this polarization mechanism. So let us go one by one. Electronic polarization happens at the level of electrons, basically, as by definition. So what it means is that, you have here, when you applying electric field, so at the level of atoms, every atom has, so if you consider atom, right, so atom has a nucleus. This is the positive core, and around it you have electrons in various shells sitting here, okay. But the center of these electrons will be coinciding with the center of these positive charges. So when you don't apply, so this is an atom, okay. So this is the core which is positively charged, and this is the cloud of electrons, cloud or sea of electrons around nucleus, right. So when E is equal to 0, mu is also equal to 0, okay. So when you apply electric field, what will happen is that this core, which is positively charged, will shift with respect to this electron cloud in such a fashion, so that there will be a, so this is the center of negative charges, that is electrons, and this is the center of positive charge, and this is happening at the scale of atom. So this is just an atom in which the sea of electron cloud, sea of electrons shifts marginally with respect to, so when you apply electric field, you create a distance delta, and you have a dipole moment upon applying electric field. Now this is a mechanism which happens at the level of atoms. The entities which are involved here are light in nature, because an atom has very low mass, and correspondingly you have to only shift a sea of electrons with respect to the atomic core. As a result, this mechanism operates at high frequencies, or you can say very, very high frequencies, typically frequencies of the order of you can say 10 to the power 15 hertz or so. So roughly 10 to the power 14, 10 to the power 15 hertz. The second mechanism which can happen, so this is present in all the materials, right? Every material has atoms. As a result, this mechanism will be present in every material, the electronic polarization. The second mechanism that we call is called as ionic polarization. Ionic polarization is, now this happens in systems where you have positive and negative ions. This happens in systems where you have positive and negative ions. So basically it occurs in containing ensemble of cations and anions. So imagine, for example, sodium chloride or any oxide that will be. So this is something that will be present in every oxide, for instance. So as a result, most dielectric materials will have this mechanism. So essentially you consider you have a positive ion, you have a negative ion, then again a positive ion, again a negative ion. So this is positive, this is negative, this is positive, this is negative, and so on and so forth. When you don't apply electric field, the distance is delta, delta, delta. So this displacement vector, this dipole moment is in this direction, this dipole moment is in this direction, both of them cancel each other. So when E is equal to 0, mu is equal to 0. When you apply electric field, what will happen? When you apply electric field, so one will become shorter and another will become longer. So this is, let us say, positive, this is negative, this is positive. So this will be mu and this will be mu 1, mu 2. So there will be an imbalance in mu's. As a result, sigma mu will not be equal to 0. So this is what is called as ionic polarization. So in this case, what is happening is the whole ion is moving with respect to another ion, and let us say it is connected by a spring sort of situation. So we can model it as if ions are connected to each other by a spring. We will do that in a little while, probably in the next class. So this will give rise to, when you apply electric field, the net dipole moment will not be equal to 0. So this is called as ionic polarization, but this happens since here the ions are moving with respect to each other, the masses involved are higher. As a result, this happens at lower frequency. So generally this will happen at frequencies of the order of approximately 10 to the 12, 13 hertz approximately, okay, depends upon the type of ion and so on and so forth. Third one is called as dipolar or orientation polarization. Okay. So this generally happens with the, let us say you have water molecule, okay. So this will happen in systems where each of the molecule itself has a dipole moment. So for example, if you look at water, okay, water is a asymmetric molecule. So generally it happens in systems with asymmetric molecules. So let us say this is O, this is H, this is H, okay. So you have a dipole moment vector here, you have a dipole moment vector here, and you can resolve the positive negative components. So as a result, it will have a net mu pointing in this direction, okay. Now this is dipole moment of one molecule. Now let us say you have these water molecules. If I contain this molecule as a sphere, so you have multiple molecules in space. So one has vector in this direction, another has vector in this direction. So when they are thermally randomized, so at a finite temperature, the dipoles are random. Even though each molecule has dipole moment, they are all randomly distributed, there is no electric field. So when E is equal to 0, sigma mu is equal to 0 because of randomization, because of random distribution of dipoles. What happens when you apply electric field? So, when electric field is applied, these then may, so let us say if electric field is in this direction, then you might have little change in orientation. So, we are, for the sake of simplicity, we are depicting in the same direction, but they'll be in different directions. So, what will happen is that if you apply electric field in this direction, there will be some change in the, so this will be for example in this direction. So, this will be in this direction, this may shift to this direction, this may shift a little bit in this direction, this may go around to this direction, so this may go to this direction. So, basically you are going to then, so when you apply electric field, you may have net dipole moment generated, and as you keep increasing the strength of electric field, you will increase more and more. So, this is called as orientation polarization. It happens at very low frequencies, okay, because of higher mass of the molecules. And then we have interfacial polarization. We have run out of time. We will discuss that in the next class, and we will further look at the frequency dependence. Okay. Thank you.